The question is to go over again quadrature modulus. And the question is just how do you map these bits into symbols? So here's our quadrature modulus. You have your bit stream coming in. And then you have this element here which are called serial tupala, which actually performs these calculations. It is mapping a certain number of symbols into appropriate point in the constellation space. Now, how many bits am I going to be mapping? Depends how many points you have chosen in the constellation space. Let's take a look at some examples. Let's say I look at this example. This is, how do we call this modulation scheme? How do we call this? This is pi over 4 shifted QPSK, right? How many points do I have? 4. So in this case, m is equal to 4. So how large is n going to be? LD of m, which is LD of 4, which is 2. So we're going to be, in this case, mapping 2 bits into a single symbol. And you can devise this mapping however you want. Let me suggest something like this. 0, 0, 0, 1, 1, 1, and 1, 0. Okay? So 2 bits are going to come in here, and then I would have to pick one of these points. Let's say 0, 1 comes. Okay? So if 0, 1 comes here, let's say 0 and then 1. So your calculator here says, okay, I want to select this guy. So I'm going to place on my in-phase branch, I'm going to place minus 1 over square root of 2. And on my quadrature phase branch, I'm going to place 1 over square root of 2. So what you're going to put here is 0,707 with minus. And here you're going to put plus 707. And then this would excite some analog filter, which you can actually either put as a real analog filter, or more likely, this is a D to A converter that's just going to be spitting out the samples of this GT of T scaled appropriately with this gain. And then you go into, you know, essentially your modulation stage where you're going to have an oscillator here. This is your cosine 2 pi at 0 t, and this is minus 90 degrees to give you here sine of 2 pi at 0 t, probably minus sine, and then you're going to take these two, add them together, and this becomes transcript, right? So that's your waveform that gets transcript. Now this is assuming that you're encoding 2 bits at a time, right? Now let's look at what happens if you're encoding, let's say, 3 bits at a time. When you do 3 bits at a time, then your m needs to be equal to what? M needs to be equal to 8, right? And therefore your n is going to be LD of 8, which is going to be equal to 3. Now to have m equal 8, I have to pick 8 points in this constellation plane. And just so that I illustrate the concepts better, I'm actually going to pick them in a very unorthodox way, right? So here's my first point. Here's my second point, third point, fourth point, fifth, and sixth, right? 7, 8. Right, so this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. I guess I'm not even following the order, right? So 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Right? You never do it this way, right? But let's do it for the sake of this example. So how does this thing work? Now, does the fact that I have 3 here change anything in the architecture of this guy? No, it's still 2-dimensional signaling. I'm going to be expressing every single point here as a combination of the two basis vectors. So let's say, for the sake of example, and I hope you copy this, so I'm going to modify this guy here. And let's say 1, 1, 1 comes. So what is it that I'm going to place here? Well, I'm going to look at the point, and I'm going to look at its projection here, and let's say this is 10, and let's say this is 2, right? So to pick this particular point, I'm going to place 10 in phase and 2 out of phase, 2 in a quadrature. And then it gets modulated, right? So what this modulator does, it actually picks appropriate point in a constellation plane, and then express that point as a function of the two orthogonal basis vectors, and then form this transmission signal as a linear combination of these two. Generally, this, because sine and cosine are forming the basis of the two-dimensional signal space, you can pick any point on this board and express it in terms of the sine and cosine. So that's why this is a general case of the modulator that can be used for QAM and QPSK, not for QAM and PSK signals alike, right? Does that answer? So you don't change because it's two-dimensional. The dimension here is added as you go to the higher dimensional signal. But as long as you stay with n equal 2, now n equal 2, meaning that you have two vectors in your basis, you can kind of you can devise schemes where you encode any number of bits per symbol. You just have to pick enough symbols in this constellation plane to accommodate a certain number of bits per symbol.
Sir, is this 10 is the amplitude value of the generated signal?
It's the amplitude value of the first vector, right? And this 2 is the amplitude value of the second vector. And that this point here is made as a combination of 10 times the first plus 2 times the second, right? Just like this one was minus 1 over square root of 2 of the first and 1 over square root of 2 of second, right? So I just picked this point. And you can kind of, any point that I place in this plane can be expressed as a linear combination of this basis vector. So I don't need more dimensions because these two vectors are orthogonal and they're spanning the entire two-dimensional space. So
but in case of multi-dimension, at that time we need more than 2 vectors.
correct. In the case of multi-dimensional space, when n is larger than 2, then you're going to have more vectors, right? And then this is not as simple, right? Your constellation ends up being pretty large, multi-dimensional. But if you remember what I went over last time, the easiest way and the practical way how we construct multi-dimensional space is we actually take this and then another one and another one and another one, all working at the different frequencies. So you can see most practical multi-dimensional space as how should I say, aggregation of many two-dimensional spaces. If you use OFDM, and typically we quote number of subcarriers, so let's say OFDM with 128 subcarriers would mean that this consists of 128 two-dimensional spaces. So you're signaling with 256 basis vectors, but really they all travel in pairs because our world is made for sine and cosine. And we can construct it probably different ways, differently than that, but most practical applications, this is how we do it. Right? Go ahead.
I have a question. So why when the composition are singular to cosine and sine? Is it because all the analog singular it can be composition sine and cosine?
Why do we use sine and cosine? Because that's a more philosophic, well, it's kind of philosophical question, but it's practical too. Practically, we know how to generate sine and cosine, right? Yeah. That's one of the things. The second thing is our circuits like sines and cosines, right? Because if you think about our circuits are performing differential calculus. They can be described with differential equations. And beautiful thing about sine and cosines, they are you take derivative of sine and cosine, and you get back sine and cosine. And that's not an accident. Why? Because sines and cosines are exponentials. Right? They're huge exponentials, right? If you think about what is sine and cosine, it's those two exponentials, right? So philosophically speaking, remember I always saying that everything in this world is exponential somehow. You know? Very few things, I shouldn't say everything, but a lot of things are exponential. So the most natural way of dealing with it is to use exponentials. So practically we deal with them, our circuits design, if you remember, if you have sine and cosines, we devise a math that allows to treat them as if they were DC. It's just that they're complex kind of DCs. Remember, all of our KVLs, KCLs, and everything works with sines and cosines in steady state as if they were DCs, DC voltages and currents. So our life is really easy with sines and cosines. That's why that's practically why we do it. But there's also more, as I said, philosophical thing is because our world is described with differential equations, and the differential equations, sines and cosines, as they travel through differential equations, they only change their magnitudes and phases. They don't change themselves. So it's they're well suited for most of the applications in this world. Now, you know, all of this may not hold true. For example, if you look at some other channels, like if you're working through optical channel, then you really just go ones and zeros, right? Light or no light. So there's no sine and cosine there. Or if you're like Dr. Murshid, he does something that's called spatial multiplexing. So over there's no sines and cosines. You're getting different dimensions by using different portions of the optical fiber. So that's why I'm kind of still dragging this psi 1 and psi 2 to handle the general case. But for most of the practical applications, at least in the current state of technology, we use sines and cosines. Just there's nothing better suited that we know of for analog waveforms. All right, so let's go back to our, remember we are now talking about reception. And the last time I said, well, the best way to receive the signal is to use matched filter. But as if you want to be strict, is I just said that, and for the most part, I ask you to believe me. And what I need to do now is to show that this is actually not one of the ways how you can demodulate, but the best possible way how you can demodulate, right? So let's take a look at properties of the matched filter. And then just so that we remember that we talked about two kinds of receivers. One was correlating receiver and matched filter. This is the difference is really more academic than practical. In most practical applications, especially where you do all of your demodulation in DSP, matched filter and correlating receiver end up implementing the same math. So they're essentially the same thing. Both of them are taking the dot product of your incoming waveform with the basis vectors. Right? And what we need to show today is that's the best way of doing it. You know, that's the best way of recognizing what has been sent. So here's here's what the main property here. If S of t, which is your transmitted signal, is corrupted with AWGN, the filter with impulse response matched to S of t to S of t maximizes signal to noise ratio. Okay? So what I'm claiming here is that there is no other filter which will have a higher signal to noise ratio at the output than what comes out of the matched filter. Right? Now, why is the signal to noise ratio important to us? Remember, because in the second stage of the reception, we'll have to decide what has been sent. And the decision is more reliable and less prone to errors, the higher the signal to noise ratio is. So we have our received signal R of t, which is going to be equal to S of t plus N of t. This is our received signal. And really, I have to say what do I mean when I say signal to noise ratio here. So let's first be very specific about what is signal to noise ratio. So here's what I have. I have my R of t coming in. Here's my filter H of t, which I can right now just say this is some general filter, and we have to demonstrate that the one that maximizes the signal to noise ratio is matched filter. And this is what I have here as the output, and this is my signal Y of t. And what I'm going to do with this Y of t, I'm going to sample that signal at some t, and I want that this sample is actually having a maximum signal to noise ratio. So let's write some math here. We have R of t given like this, and then your Y of t in general is going to be integral from 0 to t R of tau H of t minus tau d tau. What I know is this, since this is a filter linear system, the output is the convolution of the input and the impulse response of the filter, so that's the output. Now, instead of R of tau, I can put what that is. So this is integral from 0 to t, S of tau plus N of tau, multiplying H of t minus tau d tau. And what happens here, this splits into two integrals. This is an integral from 0 to t, S of tau times H of t minus tau d tau, and then plus integral from 0 to t, N of t times H of t minus tau d, N of tau. N of tau, H of t minus tau d tau. Obviously, that's a response for any t. Here, t is between 0 and capital T, where I'm making the decision, right? The t here is duration of the symbol integral. So the symbol starts arriving. I designate the beginning of the arrival as 0. And then when the time t comes, that's the end of the symbol, that's where I have to make the decision. So what do I have to deal with when the t comes, capital T comes? I get y of capital T is an integral from 0 to capital T, S of tau, H of capital T minus tau, d tau, and then plus an integral from 0 to capital T, N of tau, H of capital T minus tau d tau. Obviously, both of these are now scalar values. This is a single number, right? Because there is nothing, this is the sample of the signal at the given time, which is a capital T. So I see that the sample is going to consist of two parts. It's going to have this part here, which is deterministic, because really filter is given, signal S is given, so this is always going to give me the same value. And then I have this part here, which is going to be random. Why is this random? Because N is random. N is the noise, and it's different every time. So I can call this Ys of, this is Ys of capital T plus N, or I have it here, Yn of capital T. This is obviously due to signal, and this is due to noise. Okay? So here's how I define signal-to-noise ratio in this case. I'm going to say signal-to-noise ratio at the output of this filter, it's going to be given as ys squared at capital T divided by expected value of yn squared of capital T. Notice how I treat these two things different. This is a constant thing, right? This is not a random variable. For a given s and given h, I get a constant number here. But the downstairs, I have a random variable, so what I'm really looking here is the power of the signal upstairs and the expected value of the second moment, which is power of the random process downstairs. Right? So I'm trying to find out, so what is the problem that I'm dealing with? Well, my choice for h of t, the number of choices that I have for h of t is infinite. And pretty much I can put any given filter here. For any given filter, I'm going to get appropriate signal-to-noise ratio. And what I'm really looking for is, what is the filter that I can put here that will maximize this particular quantity? It's a little bit unusual problem from where you guys stand. I mean, it's usually we solve for some variable, right? Here, the unknown that you're solving for is a function, right? H of t is a function. So out of all possible functions, out of all possible impulse responses that I can come up with, what is the one that will give me the highest signal-to-noise output ratio? It's,
Wouldn't it be an impulse?
That's one candidate. We can put it and evaluate it. Another one would be, why isn't it, for example, sync, right? Box in a frequency domain. That would be a better choice, right? If you have S of t and S of t occupy certain space, why don't I just box that space and let that go through? And that would make the sense if I'm trying to preserve the shape of S of t. I'll comment on that later. So, but you can see there are many, many choices for h of t. What I need to find out is, I'm making this very specific. I'm saying, what is it that I'm trying to optimize? I'm trying to optimize this. Why am I trying to optimize this? It's because I want my decision to be reliable. Now, notice the nuance here. I'm not trying to bring back S of t. I don't particularly care to reconstruct S of t. You know, that's not the task. The task is, what was sent? Can I recognize what was sent? And as long as I can recognize, I can regenerate it. I know what it was. So out of a finite number of choices, which is those finite number of points in the constellation plane, I have to decide which one was generated. So go ahead.
So is ys of t squared, that's the energy of the response of the input signal?
That is this is the energy.
Of the deterministic signal?
No, it's the value of this signal here, right? Of this portion here. So look what happens. Regardless of what is the filter that I put, I'm going to get two components to my output. One of them, this is a single number, right? This whole thing is a number. Let's say, let me draw it like this, right? So this is a number. It will consist of two parts. It will be this part and that part. This part here is ys of capital T. This part here is going to be yn of capital T. Different choices for h will move this, you know, between, you know, the ratio of them, right? So I may actually have it here, right, where I let the noise go through and I attenuate my signal, or however whatever choice I select for h of t will result in a certain ratio. And I'm trying to find out what is the h of t that will maximize the ratio between the two. Right? Go ahead.
For the middle exam, and we have a question, it is calculate the capacity of the channel. the function, it is bandwidth times the log 1 plus the signal of the noise.
Yeah, I know. So you're saying this bandwidth LV 1 plus signal to noise, right?
My question is, in this function, the signal noise is the same one
As this guy.
is it same one or different?
Yes.
But
Yes.
in that question, you did mention that you said the signal noise, it won't change.
It don't change?
Yeah.
Well, you have to give me the context. I don't know why I mentioned that, this is the same signal to noise ratio. That's the one that we based our decisions on, right? And I don't know why it doesn't change. It does change. Because if there's, even if the noise is constant, depending on the attenuation of your channel, the signal will change. The signal to noise will change. Right? But that's a Shannon capacity formula. That's a little bit different than this. What is the question?
The question is determine the capacity of the channel assumed 3 dB.
I know, but that's the question in the problem, right? But what is your question about this particular thing?
About my question is, when the signal and the noise change, will the capacity of the channel will change or not?
Of course, if the signal to noise ratio changes, your ability to signal, to send more bits changes as well. And we all know that. I mean, this is what where the origination of your adaptive modulation encoding is coming from, right? As your signal to noise ratio changes, what we do in modern systems, we change your constellation, and as a result, your data rate goes down, even though the bandwidth that you use is the same. And what is the example of that? If you're in Wi-Fi environment, for example, and you want to get a real good throughput, you look where the access point and you go right there. Because if you don't have enough signal to noise ratio, the modulation scheme will be selected to be, let's say, BPSK or QPSK as opposed to 16 QAM or 64 QAM. Right? So that's directly proportional. It's just that the relationship is logarithmic. But that's a little bit, off the main topic. The main topic here is I'm feeding my signal plus noise in the filter, and I'm sampling it at T. And what it turns out that sample value is going to have two components. One is going to be due to signal, and the other one is going to be due to noise. And the question is, how do I select h of t to reduce the noise as much as I can while preserving the signal as much as I can, right?
But I thought the whole concept behind the mesh filter was it was tailored just specifically for that signal. So it's already picked, isn't it?
Well, that's what you're still believing. What I'm kind of, I'm gonna say it is mesh filter is one way of demodulating. We have no doubts about it. What I'm trying to say, well, is there a better way?
Okay.
Right? And what I want to show you here is there isn't. And then this will result in a whole bunch of math, and you're going to say, okay, yeah, you showed it, but so what, right? What insight do I get? And then we're going to look at the same thing in the frequency domain, and you're going to understand exactly what mesh filter does. And not only that you're going to understand what it does, you're going to see your good old friend. And I'm going to show, and this is something that is consistent across many, many different areas. Whenever you try to optimize for signal to noise ratio, you're going to end up with a similar kind of behavior. And I'll point it out at the end of the journey. And then just to give you a preview, you're going to start understanding optimum ratio combining. You're going to understand a lot of things from adaptive filtering, why certain things work certain ways. Right? Go ahead.
So basically that dial, that imaginary dial you're saying that goes up and down, that the noise and signal. So if it goes completely up, so it's everything that contributes towards the signal, and that's basically the basis, right?
That would be an ideal case, right? That would be dream scenario, and if we can get there, it would be awesome. But we will show that you cannot really get there, and that the best you can do is actually your meshed filter, and it would put this dial highest as it can go, but higher than that you cannot. You know, it could also establish the limit on how good your demodulation can be. Right. All right. So let's work this little. So that's what I'm trying to optimize. So how do I do that? Well, let's first look at this ys of t. Ys square of t is going to be equal to integral from 0 to t s of tau h of capital T minus tau d tau. As this is, everything is deterministic here, all I do is I square this and I say that's what it is. Give me h of tau or h of t, and I'll be able to always tell you what this is. So here the work is done. But let's take a look at our denominator. Expected value of yn squared of t is going to be expected value. If I want to square this, I'm going to say this is an integral 0 to t, when tau 1 goes from 0 to t, n of tau 1, h of t minus tau 1, d tau 1. So that's the first yn. And then the second one is going to be integral when tau 2 goes from 0 to t, n of tau 2, h of t minus tau 2, d tau 2, and then expected value of this. And just like in many other cases, you know, whenever you get something like this, it always benefits you to reshuffle the integration and all these linear operators. So what I'm going to do here, I'm going to take this integration outside. So this becomes tau 1 goes from 0 to t, integral when tau 2 goes from 0 to t. And then I have expected value of n of tau 1, n of tau 2, and then h of t minus tau 1, h of t minus tau 2, d tau 1, d tau 2. Everything here is a linear operator, so I have to, they're all interchangeable, but you have to be careful. What does each one of them operate on? Expected value, these things are not random. These are given impulse responses, so they go outside of expectation. And the only thing that is random is this noise here. Now let me ask you this, what do I know about the noise?
Should be this 0 everywhere except for T1 equals T2.
Okay, it should be 0 except when T1. So what is it that I know? I know that the noise is white, and what that means, it has a constant power spectral density. And as a result, what does the autocorrelation function look like? Since autocorrelation function is the inverse Fourier transform of the power spectral density. If power spectral density is constant, autocorrelation function is delta, right? Delta, right? Because that's the Fourier transform thing. So this thing here is n0 over 2 delta of tau 1 minus tau 2. Right? That's an autocorrelation function. And 0 over 2 is the power spectral density, double-sided. And then inverse Fourier transform of this is this, and then the delta function. So now, what I have here is I do have a two-dimensional integral. I integrate relative to tau 1 and tau 2. But it is really not two-dimensional, right? Because the only place where the subintegral function is non-zero is when tau 1 is equal to tau 2, right? So here's what I have. I have, essentially, I need to integrate over this entire plane, tau 1 and tau 2. But what this tells me, don't bother integrate anywhere but when tau 1 is equal to tau 2. So this is really just a line integral of a single variable, because I'm integrating on this one particular line. So to make a long story short, this now becomes an integral when tau goes from 0 to t, n0 over 2 delta of tau. Just make sure that or let me I can just say n0 over 2, and then here, when tau 1 is equal to tau 2, this becomes h squared of tau minus tau 1 of tau d tau. So that's what this integral boils down to. Okay, so now n0 over 2 can go outside, and I have that this is n0 over 2. Integral tau goes from 0 to capital T h squared of t minus capital T minus tau d tau. So that's the expected value of yn squared of t. And from those two, I can therefore form the signal-to-noise ratio. Signal-to-noise ratio at the output is going to be 2 over n0 from downstairs, when this goes downstairs. And then upstairs, I'm going to have integral from 0 to t, s of tau, h of t minus tau squared. And downstairs, I'm going to have integral from 0 to t, h squared of t minus tau d tau. Right. So that's a little bit better, because now you can see that I have eliminated expected value, and this tells me, you know, beautifully that if you give me h of t, if you give me a filter, I'll tell you what the signal to noise output ratio. So I need to search over all possible filters to get the one that has the best signal to noise ratio. So let's leave this for a second. I need to bring in some math here that will look a little bit intimidating, but you actually know it very well. It's just that you're not familiar with this kind of formulation, right? But this is something that you've seen in high school, or maybe even early, if you went into AP class. So here is something that's called Cauchy Schwarz. I mean, Schwarz inequality, right? Inequality. Let's look at two functions, g1 of t and g2 of t on interval I, right? Then here's the Cauchy-Schwarz inequality. This one says the magnitude of g1 of t in dot product with g2 of t squared is smaller than, I should say, the norm. The norm of g1 of t squared times the g2 of t squared. So that's what this inequality says. Okay. Now this is something that you look at and you say, well, how is this even? You know, what does this even mean? But so far, we've learned to look at our functions on a given interval as vectors, right? So let's try to understand where is this coming from if g1 and g2 were just two vectors. So let's take a look at two vectors, right? Let's say this is a vector g1 and this is a vector g2. So tell me, g1 in dot product with g2, what is this equal to? It's going to be magnitude of g1 times magnitude of g2 times cosine of the angle between g1 and g2. Okay? So g1 by g in dot product with g2 is just a single number, right? That's a number, right? So I can take the magnitude of that number and I can square the guy. And you can see that this is G1 squared, magnitude of G2 squared, times the cosine squared of the angle between G1 and G2. Now, if you look at this a little bit closely, what is it one thing that we know about cosine? It's always smaller than 1, right? So, this is always smaller than just G1 magnitude squared times G2 magnitude squared. Okay? Because this is always smaller than 1. So if I just take the first one and the second one, then you end up with G1 times dotted with G2 squared is smaller than the magnitude of G1 squared times the magnitude of G2 squared. Tell me, when does equality hold? When they are parallel. So equality holds when G1 is, for example, equal to K times G2, right? When they're parallel. They're either in the same direction, or when means K is positive, or they're in the opposite direction, meaning K is negative. So now, since some time ago, we have established complete duality between our functional space and this vector space, we show that the functional space on a given interval forms a vector space, then I can claim something like this, right? That the dot product, magnitude of the dot product between two functions is smaller than the norm of the first function squared, norm of the second function squared. So that's what is called Cauchy-Schwarz inequality. It's one of those famous inequalities. So let's see if we can apply that to our expression here. So remember, what I'm trying to maximize is the signal-to-noise ratio at the output. So if I apply this relationship to that expression over there, so let me do this. If I look at this thing here, let G1 of t equal to S of t, and G2 of t equal to H of t minus t. Or maybe, just for clarity of notation, make all of these guys tau. Tau, tau, tau. So now, I can write the signal-to-noise ratio at the output. What you see upstairs is really dot product of the two functions squared, right? So I can say this is equal to, or this is smaller. Instead of seeing this as a dot product, I can say it's smaller than the norm of the first one squared times the norm of the second one squared. So the signal-to-noise ratio is always going to be smaller than 2 over n0, integral from 0 to t, s squared of tau, d tau, times integral from 0 to t, h of t minus tau, squared, d tau, divided by integral from 0 to t, h squared of t minus tau d tau. What's so cool about this? This whole thing disappears, right? So I get that my signal-to-noise ratio at the output is always smaller or equal than this. Now, this guy here is our friend. What is this?
Energy of the signal.
Energy of the signal. So it's 2 epsilon s over n0. So this is where my slider sits. This is the highest up that I can push slider. It's always going to be smaller than this. My signal-to-noise ratio at the output is always going to be smaller than this. when is it going to be equal? The equality holds, that's when it's maximum, right? It's always smaller than that, so the upper bound is when it's equal. The maximum value of signal to noise ratio output is equal to epsilon s over n0, and it occurs when? When these two are parallel, right? How are they parallel? Well, you can say s of tau, or I can say like this: s of tau is equal to k of h of t minus tau, or I can say h of tau, which is the same thing, is k times s of t minus tau. Well, what is this? I'm saying that my impulse response has to be equal to this. Well, how do we call the filter where the impulse response is equal to your signal flipped and shifted?
Match.
So the filter needs to be matched filter. Okay? So that's a conclusion. Out of all possible choices for the filter that I have at the receiver side, the one that maximizes my signal to output noise ratio is going to be matched filter. And in all cases, if my filter is matched to the signal, the output signal to noise ratio is going to be 2 times the energy of the signal divided by the power spectral density of the noise. Okay, so that's a proof, right? Out of all possible filters that I can use to demodulate, the one that performs the best when it comes to the maximization of the signal to noise ratio is matched filter. The question is why, right? Why? I mean, what does it do physically that makes this happen, right? So in order to understand why is matched filter the best, let's take a look at what happens in a frequency domain. Because from here, I mean, even if you trust the proof, you still don't know, you still don't see why is that the case, right? Why is the matched filter the best? So let's just demonstrate why is that the case. So to refresh the settings, here is S of t. It comes in, it's corrupted with your AWGN noise. And here's the filter here. That's your matched filter. And I'm going to sample this at the capital T to get my ys of t plus yn of t with the maximum signal to noise ratio, the output, equal to epsilon s over 0, right? That's my maximum signal to noise ratio, knowing that my h of t is going to be equal to k times s of t minus t, right? The k here is irrelevant because that's some arbitrary gain, but whatever applies to signal applies to noise as well. Therefore, your signal to noise ratio stays the same regardless of what the k is. So a lot of times we just neglect it and treat it as 1. All right, so let's look what happens here. H of t is s of t minus capital T. Therefore, your h of f, which is, if this is an impulse response, how do we call h of f? Frequency response. Fourier transform of an impulse response. This is a frequency response. Is integral when t goes from minus infinity to plus infinity. H of t e to the minus j 2 pi ft dt. Let me substitute what h of t is. So this becomes integral when t goes from minus infinity to plus infinity. S of t minus t e to the minus j 2 pi ft dt. So that's what I need to calculate. So now I can use the substitution. Instead of t minus capital T minus t, I can introduce the substitution. Let's call t minus little t as nu. From here, you can see that d nu is equal to minus dt. And you can see that, what do I need here? T is equal to capital T minus nu. So t is equal to capital T minus nu. So now if I substitute that in here, I get that my h of f is equal to integral. When t is in minus infinity, where is nu? When this is minus infinity, where is nu? Plus infinity, right? So nu goes from plus infinity to minus infinity. S of nu, right? Because this t minus t is equal to nu. And then I have e to the minus j 2 pi f. Instead of little t, I can write capital T minus nu. T minus nu. And then instead of dt, I have minus d nu. Right? Minus d nu. So my h of f becomes equal to what? Integral. Because of this minus here, I'm going to split my borders back again. So nu goes from minus infinity to plus infinity. S of nu, e to the minus j 2 pi f plus nu, d nu. And what I have outside, e to the minus j 2 pi f capital T, because the capital T does not depend on nu, so I can take it outside of the integral, right? Now, tell me what this is.
Inverse Fourier.
Is it inverse Fourier? Because remember, you're not going over f, you're going over nu. I can put t back here if that would make you.
It's got a plus.
H conjugate.
Yeah, it's almost Fourier transform, it's just its complex conjugate, right? Because it's flipped this sign. So this is here S of f complex conjugate e to the minus j 2 pi f t. So that's how the frequency response of the matched filter look like. So what is strange about it? Let's just look at what happens here. If you're, let's say your this is your n0 over 2. And let's say your signal looks like this. So this thing here is the magnitude of S of f. Well, this is the same thing as the magnitude of h of f. Right? Because the magnitude, if you take the magnitude of the left-hand side and the magnitude of the right-hand side, you get that your h of f is the magnitude of S of f. They're the same. Okay? So this is how your matched filter will look like in a frequency domain. So let's say, let me just make sure. Let me just do it this way. So this is the magnitude of h of S of f, and this is how your matched filter looks like. So what's the big aha factor here? What's the big thing that should jump right away here? The big thing that should jump right away is that this is not an ideal filter, right? What does the ideal filter look like? Let's say I'm doing analog communication and I'm trying to receive this signal S of f. What would be my inclination to do in terms of filtering? To put the box like this, right? And I would say, let the signal go through and reject as much noise as possible. What does the ideal filter look like? Remember communication theory. What is ideal filter? It's flat across the top. It's flat in the magnitude response, and it has a linear phase. But it's flat in the magnitude response, so that it does not distort the signal itself. Matched filter is not an ideal filter. Matched filter is frequency selective itself. What does that mean? It does not treat all the signal components equally. It amplifies these guys and attenuates these guys and completely rejects everything outside of the signal. So you have a filter now that looks at across the board of different frequencies that exist in a signal itself, and then it looks at the areas where the signal to noise ratio is high, and it amplifies those areas. And then the areas where the signal to noise ratio is low, it attenuates these areas. And the areas where signal to noise ratio is 0, it filters them out completely, right? So where the signal is good, I want more of that. Where signal is bad, give me less of them. And when there's no signal, don't even let anything go through. So this filter is selective. What does this mean? If I take a signal and I run it through a frequency selective filter, what happens to the signal? What comes out is different what came in. The signal gets distorted, right? Why? Because the fine relationship between sinusoidals that built this signal in the first place is now disturbed by the very filter that I'm using to demodulate, right? Because I'm taking the components, for example, that are here, and I'm amplifying them, and taking the other components and I'm attenuating them. So what came out of the mesh filter is going to be different than the signal itself. But that's acceptable here. Why is it acceptable? Because I'm not really concerned about preserving the signal. What I'm trying to do is maximize signal to noise ratio. So I'm trying to amplify my signal as much without amplifying the noise. So what I'm doing is I'm amplifying the areas of the signal where the signal to noise ratio is good, attenuating the areas of the signal where the signal to noise ratio is poor, and completely getting rid of the noise. Now, that's what the mesh filter does. And that's what we find quite a bit. Remember, for those who took RF propagation, we have a similar scenario when we are receiving the signal from multiple branches. The signal to noise ratio in each branch was different. How do we combine them to maximize signal to noise ratio? You take the best branch and use the most of it. And you take the least branch and use the least of it, right? So it's almost like you treat them as like a stepchildren or some sort. If it's good, you feed it more, right? And if it's bad, you feed it less. And that's what happens here. And that's always the case going to be in a lot of problems, that you encounter, in various courses. You're going to find the task of maximizing signal to noise ratio. That's a really different task than preserving the signal. And whenever you try to maximize signal to noise ratio, it's always going to be, where is it good? Give me more of that, and where it's bad, give me less of that. You're not going to try to equalize anything. You're really greedy here. You're trying to maximize and use where it's good. You're going to use more of it. And the consequence of that is the signal is not going to be preserved. But since that's not major objective, we just need to make sure that we know how to make decisions. So just to give you a blunt example, if my signal S of t is pulse, and I match it with a meshed filter, what comes out of the filter is not going to be pulse. It's going to be a triangle. Okay? So it's going to be completely different. But I have no problem, because at the point where I look at the triangle, at the end of the t, that's going to be the highest signal to noise ratio that I can make, that I can have. And my decision is going to be the best one I could possibly make. Now, what is the output signal to noise ratio in this case? Let's just calculate it. So, output signal to noise ratio Ys of t is going to be inverse Fourier transform of y of f, right? Where y of f is going to be product of s of f and h of f, right? I can say here y of t is convolution of s of t and h of t. or I can say y of f is s of f multiplying h of f, right? We are both familiar with this. These are Fourier transform pairs, right? So I can say ys of t is this. So it's going to be Fourier inverse of s of f times h of f. So this becomes an integral from minus infinity to plus infinity. S of f. Now h of f is s complex conjugate of f times e to the minus j 2 pi f capital T. And then I have to put my Fourier stuff, so it's hj 2 pi f t df. Right? So that's the inverse Fourier transform. Now, I can write this as inverse, or I already, so I can look at this part here, and I can simplify, so this is f goes from minus infinity to plus infinity. What is s of f times s complex conjugate of f?
Square.
It's the square of the magnitude, right? So this is s of f magnitude squared e to the j 2 pi f of t minus capital T df, right? And you can see this is so that's what inverse Fourier transform is. If I take ys, but I sample it at capital T, this becomes an integral when f goes from minus infinity to plus infinity, s of f magnitude squared. When t becomes capital T, what happens to this exponential? 1. So it's df. Now tell me what this is.
Energy.
If I take the integral area under the curve of the square of the power spectral density, this is energy. So this is my epsilon s. Now calculated in a frequency domain, right? Not in a time domain. We are accustomed to take s squared of t dt, but we also demonstrate that you can do it in a frequency domain. Now how about the power of the noise? Power of the noise, I can calculate that as using my f goes from minus infinity to plus infinity, Sn of f times h of f, what? Magnitude squared df, right? Remember this relationship? Power spectral density of the noise is going to be power spectral density of the noise at the input times the magnitude square of the filter, and then the total noise power is the area under the curve of the power spectral density. So now, if I substitute what this is, I get power of the noise is integral when f goes from minus infinity to plus infinity. What's the power spectral density of the noise at the input? And 0 over 2, right? Because it's a white noise. And then this is h of f squared. But h of f is this. So if I take the magnitude of this is magnitude of s of f squared, right? So this ends up being magnitude of s of f magnitude squared df. So this is n0 over 2 taken outside. What is left? Well, the same as this, right? So this is going to be energy. And then if I look at signal to noise ratio, it's going to be ys of t squared over power of the noise, which ys of squared is epsilon s squared divided by power of the noise, which is n0 over 2 epsilon s, which is 2 epsilon s over n0. So, and it better be that, because we know that from the time domain, but now it's kind of shown that the same thing has to hold just by looking at it frequency domain. So what this power here, it's essentially what goes through this filter, right? This section. And then the energy of the signal is, this goes through this filter and gets shaped appropriately, and then you get that under the curve. So the way how you can think of this is you have a filter, you have a signal, it's shaped somehow in the frequency domain. You're making a door that this signal goes through. You're fitting the door right to the signal, right? So wherever the signal is told, the door has the exact shape of the signal. So the signal just squeezes through this door, right? And the noise also squeezes, right? But the portions where the signal to noise ratio is high, those are really amplified by the filter. These guys are attenuated, and then these are eliminated. So this door is really tailor-made to this particular signal. That's why it maximizes signal to noise ratio. Go ahead.
So how did you get the shape for the magnitude of S of F?
Just
Arbitrary?
I mean, whatever it is, right?
Okay.
Whatever it is. This is Gaussian pulse. You know, if you signal, you can try to do that. If your signal is Gaussian in a time domain, its frequency domain looks Gaussian. So that's what I'm drawing. But it can be anything, right? If you signal with, let's say, square pulses in time domain, then guess what? Your matched filter is also going to be square pulse. So in the frequency domain, you're going to have sync here, and your matched filter is also going to be a sync filter. So it's going to make a door that will let the signal go through and all of its tentacles, right, all go through. And then the noise is going to be reduced as much as possible. Right. Okay, so let's see next. So I assume that by now you're fairly convinced that the matched filter is the best filter we can use to improve our decision making. So at this point we're taking care of the first part, and this is demodulation. So let me go back and refresh your memory on how we receive digital signals. You can see the reception is essentially two steps. First step is demodulation, which is projection of your incoming signal along the direction of the basis vectors. We do that through correlation of the signal with the basis vectors, which we now understand as filtering with a matched filter. And not only that we understand that this is equivalent to correlation, but we also understand that this is best you can do in terms of the signal to noise ratio maximization. And now, after that, we have to look at what came out of these mesh filters and make a decision. And this is what the second step that we call detection. So let me draw that in just a second. So here's how our communication, digital communication works. You have your transmitter. This is your line, your channel. This is, you have selected SM of T, one of possible M symbols. M goes from 1 to capital M. Now, along the line, you picked up the noise, N of T, which has a WGM property. And here you have your demodulator. And what does the demodulator do? It actually does this matched filtering. And you're going to have multiple branches here. How many correlations or how many mesh filters do you need to have here?
2.
2. Why 2?
Because that's the order of our, we're using
okay,
2.
So really N,
N.
right? N filters. Right, you're gonna, where N is the dimension of your signaling space. So if you're having, you know, one-dimensional signaling like pulse amplitude modulation, you're gonna have one filter. But if you have two-dimensional signaling, you're gonna have 2. If you have more dimensional signaling, you're gonna have more. But you're gonna have N in general case. And out of each one of them, you're gonna get the component. So you're gonna have a vector R, which is gonna be N by 1 vector. It will have N components, where every one component represents the projection of this signal here, R of T, along the direction of the particular basis signal or basis vector. This is going to be now a vector that I'm going to feed into something that's called detector. And detect is going to make a decision. And what is the detector going to say? Well, this was Sn, or let me say Sn. So this is a decision. Okay? Hopefully, Sn with a hat is the same as Sm, in which case we made a good decision, we made a correct decision. However, depending on your signal-to-noise ratio, essentially how drunk is the guy throwing the dart, you may actually make erroneous decision, and you may be sending S1 of t, and after all of this, your detector says, look, it looks like S2 of t, and it makes the decision that is erroneous. What our task is going to be is first to devise rules how the decision is going to be made. Right? There's different strategies that we can use for decision-making process. And depending on a decision-making strategy, we're going to calculate the probability of making a correct decision. We're going to try to quantify what is the relationship between signal-to-noise ratio at this point or this point, whichever one you want to utilize. What is the relationship between signal-to-noise ratio at this point and your probability of making an erroneous decision? And that's going to be a relationship that will characterize this receiver at a macroscopic level, end-to-end level. Right? And this is usually come up in the form of some curves that will tell us if I want to make my decision-making process this good, this is what I need to provide the input in terms of signal-to-noise ratio to make sure that my receiver performs properly. And guess what? These signal-to-noise ratios that I'm talking about here, these are the same signal-to-noise ratios that I'm talking about in PCS and other classes when I say the receiver comes with a signal-to-noise ratio required for its proper operation that goes into receiver sensitivity calculations. This is where we look at macroscopic look and say, okay, for this to work properly, which is functional modulation coding and all that, I need to provide 12 dBs here or 35 dBs or whatever is the ratio that I need to provide. Okay, so, all right, so let's stop here. That's where we're going to continue. Next time when you come, we're going to actually devise a strategy and start calculating big error or probability of making an error, single error. So translating into big error. Now we've specified the midterm for this one. It's on April 4th.
Do you have any homework?